In this video, we're going to be talking about buoyant forces and Archimedes' principle. We have two sample problems here. The first one starts out with a 10 kilogram box with a volume of 0.2 meters cubed that's submerged into water. What is the resulting net force? So we have a container. It is filled with some water, and we have a box inside of it. And we have some forces acting on it. We have the force of gravity, which is mg as usual. And then using Archimedes' principle, the amount of water that is displaced will provide that buoyant force based on the amount of weight of that particular chunk of water. And the way we find that buoyant force is based on the density, G value, and the volume of water. Now, what we can do is take a look at these two forces, and we're looking for the resulting net force. So we don't really know if the object is at rest, sinking, or getting pushed towards a surface. So we're going to go ahead and figure that out. So we have FB minus FG equal to our net force. So for our buoyant force, we have rho, which is the density of water, which is a constant of 1,000 kilograms per meter cubed, times 9.8 times the volume of 0.2, and then minus our mg, which is 10 times 9.8. So all we really need to do is find the product of those two and then subtract, and then we get 1,960 newtons minus the 98 newtons of weight, and that gives us our final answer of 1,862 newtons as our final net force, and that is directed upwards because that was from our buoyant force. So it looks like the object is going to get accelerated up towards the surface because our FB is clearly much greater than our mg. So the first thing you want to do is definitely draw out your diagram, which is going to be pretty similar in most cases. In this one, we just have our buoyant force upwards and our FG straight down, and then we just subtracted them because they're in opposite directions to find our net force. So let's go ahead and take a look at our second case now. Let's go ahead and separate this one out. And we have an object that's 5 kilograms and has an initial acceleration of 4 meters per second squared after being submerged in water. What is its volume? So in this one, we have a similar case, except it's giving us some kind of acceleration. We know the forces are unbalanced, and we're working our way around to solve for the volume. So we have a case where we have the buoyant force being counteracted by mg, and that equals the net force. Now we know the net force from Newton's second law is mass times acceleration, so I'm going to go ahead and slide that in. We have a mass of 5 kilograms, and we know we have some kind of initial acceleration of 4 meters per second squared. So let's go ahead and take care of that early on. Now for our buoyant force, we have this formula just as we used before. We have the rho of water, 1,000, our constant 9.8, and some kind of unknown volume minus the mass, times 9.8, and this side 5 times 20, or it's 5 times 4 is 20 newtons. So what we can do is we can go ahead and simplify the look of our problem a little bit. 1,000 times 9.8 is 980 with our coefficient as our coefficient in front of the v. And then we have 5 times 9.8, which is 49. Let's go ahead and add that 49 to both sides. And we're just about done with the problem now. All we have to do is cancel out the 980 by dividing on both sides, and then we have a final volume of 0.007 meters cubed. So in this case, we use the same ideas as the previous one, as in we have our two forces, our buoyant force up and our force of gravity down, using Archimedes Principle, except on this side, our net force, we had to break it up into our two components, mass and acceleration, and then we had an unknown v on this side. So just a little bit more algebra, but very similar ideas to solve for our second solution as well. So I hope that was helpful in helping you solve some buoyant force and Archimedes Principle type problems. Thank you for watching and listening.